Okay, for number 2, we want to tell which of these following series diverges. So we're just going to go through them one by one here and show you the tests for how you can do this. So for the first one here, we have the infinite series from n equals 1 to infinity of 3 over pi, all raised to the n power. So hopefully you recognize that this form right here looks like a geometric series. And for a geometric series to converge or diverge, the only thing that's important is what ratio is inside, or what fraction is inside that's raised to the n power. So in that case, we're looking at the quantity 3 over pi. And for a geometric series, if this fraction is less than 1, we have convergence. If it's greater than or equal to 1, we have divergence. And then keep in mind, that's absolute value of that. So in this case, 3 over pi is less than 1 because pi is bigger than 3. Therefore, this fraction is less than 1, and therefore by the geometric series test, this would converge. So this does not diverge. Okay, the second one here, we have 1 over the square root of n cubed plus 1. For this one, you can basically think of this as a p series because we have n cubed plus 1. It's basically a power 3 type thing here. But, I mean, you could easily compare it to something along the lines of that, n to the 3 halves. This is of the order 3 halves for the degree of the denominator. And you can see by p series, that's greater than 1, and this is definitely going to converge also. Okay, for the third one, we have an alternating series, and we have ln n in the denominator. So, normally speaking, you would know that the series, if we just had 1 over ln n, and this wasn't alternating, that this would definitely diverge because ln n is smaller than any power of n. And you could even test something like 1 over n to the 1/2. You definitely know that this series diverges because of the p series, but ln n is even smaller than n to the 1/2. So if the denominator is even smaller here, this is going to be even bigger, which certainly means that that's going to diverge too. But we have an alternating series here. So remember, for the alternating series test, we have 2 conditions that must be true. We know that every subsequent term, the absolute value, has to be less than the one before it. Or I should say less than or equal to, or just less than. So the terms have to be decreasing, that's what that means. And we know that the limit as n goes to infinity of the series has to be 0. So if those 2 things are true, then this would converge by the alternating series test. So here, for this one, we're looking at the absolute value, meaning not the alternating part. We're just looking at 1 over ln n. Well, ln n is a strictly increasing function. If you plug in bigger n's, ln of n is bigger. Therefore, when you plug in a 1 higher n into this, the denominator is going to be bigger, meaning the function is going to be smaller. So number 1 is definitely true. Is the limit 0? Well, as n goes to infinity, ln n is also infinity, and you get 1 over a number approaching infinity. That is 0. So those are both true. Therefore, that converges by the alternating series test. Remember, we're looking for which one diverges. Okay, as we move on to letter D, we have the infinite series from 2 to infinity of 3 over n ln n. So if we have this here, 3 over n ln n, that's one that's not easy to do by comparison. One of a few types of series that is not easy to do by comparison. Instead, what you want to recognize here is that if we converted this to a function of x and integrated it, we could put the 3 outside. we could definitely use the integral test here. Now remember, for the integral test, we want to go from, in this case, we're starting at 2. So remember that the integral test says that if you take the improper integral from 2 to infinity, and you find that it is finite, then we have a convergent series. If you find that it's infinite, we have a divergent series. Now, for oftentimes many of your functions will be a little bit too complex to use the integral test on. However, the integral test is one of the clearest and easiest tests to use, as long as what you have is something that you know how to take the integral of. In this case, we definitely have that. And why is that? Because we have the derivative of one part of this function in the function. The derivative of ln x is 1 over x. We have that there, and that tells us that this is perfect for a u substitution. So we're going to say u equals ln x. Do our standard u substitution. Du is going to be 1 over x dx. And if you notice, we have 1 over x dx right here in this. So after doing our substitution, we're going to get that we just have 1 over u du. Because this will all have turned into du, the ln x just becomes u. And now we have this. And of course, this is the integral we all know. And this is going to be 3 ln of u from 2 to infinity. But remember that you can't plug in 2 and infinity yet, because that was in terms of x. So you have to plug back in. And we're going to get 3 ln of ln of x, because u was ln of x. So this improper integral has come down to this here, and we just need to see, is this finite or infinite? Well, when you plug in infinity, or a number approaching infinity, ln of infinity approaches infinity, and therefore this ln of infinity also approaches infinity 3 times, still that. So we're definitely getting an infinite number. And when we plug in 2, we're just going to get some constant. So I'm not going to bother, figuring out what that is. Because bottom line is, that is infinite. So what this tells us is if the improper integral gives you an infinite result, or just anything basically that's not finite, whether it does not exist or infinite, we know that this series diverges. So that is the series that diverges. Real quickly, let me go over the last one though, how you could show that converges. So here we have the series from 1 to infinity, n cubed over e to the n. This one would be easiest to do just by the comparison test, or perhaps the ratio test. There's a variety of different ways you can do that one. Let me show it by ratio test. I feel like that would be the most conclusive and easiest to do here. So if we do the ratio test, remember that the ratio test says we need the absolute value of the ratio of the n plus 1th term to the nth term to be less than 1. And then this converges. So what we can do here is just put the n plus 1th term and then instead of dividing by the nth term, we can just multiply by the reciprocal of the nth term. So we multiply by the reciprocal of just with n, which is what our series is in the first place. Sorry, and this needed to be limit as n goes to infinity. So you can see here, we basically get a couple of things happening. And at this point, we can kind of drop the, we can drop the absolute value, because n was always going to be positive, e to the n is always positive, so those work out pretty nicely, in fact. So we have n plus 1 cubed over n cubed. I'm grouping the algebraic parts together and the exponential parts together. Now e to the n plus 1, if we have an e to the n on top, that almost completely cancels out. This would be left with just an e, because remember, e to the n plus 1 is like e times e to the n. So that part would cancel out with that, but we still have an e left on the denominator. So finally, we're doing the limit as n goes to infinity. These two right here are same degree n. They're both n cubed. So all we need to do is think about what's the coefficient on the n cubed term. Well, if you were to expand this one out, it would still start with n cubed. You have n cubed on the denominator, therefore the limit is 1. So finally we get down to 1 over e. 1 over e is definitely less than 1, so therefore this converges by the ratio test. So this one here, 3 over n ln n, that was our only series that diverged.